Hello, today I'm going to talk to you about Lewis structures, and what I've shown here is a Lewis dot structure for every element in groups 1A through 8A, so there's no transition metals here. But what you'll see is that there's a dot, just one on every element in the first column, 2 in every element on the second column, 3, 4, and so on until we get up to 8 for everything in column 8A, with the exception of helium. Okay, so each of these dots represents a valence electron, or one of those ones in the outer shell for that atom. So you'll notice that they generally are clustered in pairs on the 4 sides of the element. That's generally how we write them. And it's possible to draw Lewis structures for each of the atoms like this, but most of what we're going to do in this lesson is talk about how to draw it for covalent compounds. Okay, so these are the steps that you will go through. They're a lot of steps, okay? I'm going to do some examples and basically go through that process for you. And so you'll have this as a reference, but I'm not going to spend time reading this to you. You can read, and then you have all of that information there in front of you. Okay, so the first example we're going to do is PCl3. Okay, the P is likely going to go in the middle, all right, because it is less electronegative than chloride. Remember, we covered electronegativity in the periodic trends chapter. The closer it is to fluorine, the more electronegative it is. So chlorine is more electronegative than phosphorus. And also, we tend to end up with the thing that we only have one of. That is usually what ends up in the middle. Okay, so here, let's add up the valence electrons. So phosphorus has 5, because it's in column 5A. Chlorine has 7, because it's in 7A. And there are 3 chlorines in our molecule. That's what this little 3 here means. All right, so that's 21 electrons from all those chlorines. So 5 plus 21 gives us 26 total valence electrons. So that is how many dots we are going to need to have in our final structure. All right, we're going to put phosphorus in the middle, like I said, chlorine around the sides, and the first thing that we're going to do is make a bond with each of those chlorines to the phosphorus. Okay, a bond, I prefer to draw them with lines. You can do 2 dots for a bond as well, but one line represents 2 dots or 2 valence electrons. Remember, a single bond is the sharing of 2 electrons, right? So we've now used 2, 4, 6 electrons, which means we have 20 more that we need to put around. So I start with the elements on the outside, or the atoms on the outside, and fill their octet, okay? So each of these chlorines has 2 from the bond, and so we'll add 6 more to give it a full octet, 6 more to that one, 6 more to that one, all right? That gives us 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. We have 2 more left, all right? And phosphorus doesn't yet have a full octet, so that's where the last 2 electrons are going to go. So now phosphorus has 2, 4, 6, 8, okay? ClO3 minus. So this is a polyatomic ion. There's just one extra little step we're going to do, but not a whole lot changes when it's an ion. Okay, so let's add up the valence electrons. 7 for chlorine, 6 for each of our 3 oxygens is 18. And the negative charge means this has 1 extra electron compared to what it would normally have. So that gives us an extra one. We add those together and we get 26. All right. In this case, chlorine is less electronegative than oxygen, so that will go in the middle. And then we'll put our 3 oxygens around it, make our 3 bonds. Okay, that is 6 electrons. We have 20 left. So we'll do 6 there. 6 there is 12. 6 more is 18. And again, we have 2 left, but chlorine doesn't yet have a full octet, so that's where the last one will go. All right, and then the one other thing we have to do, because this is an ion, we put it in brackets, and we put the charge outside, right? So, easy enough. All right, CO2. Let's add up our valence electrons. Carbon has 4. Each oxygen has 6, so that's 12 total for the oxygens. 4 plus 12 is 16. All right, oxygen is more electronegative than carbon, so carbon will go in the middle, and then we'll put our oxygens on either side. So we'll start with a single bond for each. Okay, that is 2, 4 electrons, so we have 12 more. So put 6 on each of our oxygens, and now we've used all the available valence electrons, okay? But there's a problem. Carbon does not have a full octet yet, So if we do additional sharing, we can move some electrons in from each of our oxygens, okay, and the result will be that we get 2 double bonds. Now carbon has 4 bonds, so that's 8 electrons, so it's got a full octet. Each oxygen has 2 bonds and 2 lone pairs, so that makes 8 for each of them, okay? So it can be a little tricky to know when to make double bonds, but as a general rule, if you've used all of your valence electrons and some of your atoms still don't have a full octet, you need to do more sharing, which means making either double or sometimes even triple bonds. Okay, in this case, double was enough. All right, so our next topic is resonance structures, and this is an extension topic. It will not be on your mastery or on the test, but is a really, I think, kind of an interesting way to draw Lewis structures, and very important if you want to go on to do chemistry or biology after high school or in AP. Okay, so let's go through the steps just like we did before. So we have SO2, right? We'll add up our valence electrons, 6 for sulfur, 6 for each oxygen makes 12, so that's 18 total. Okay, the sulfur will go in the middle. It's less electronegative than the oxygen. We'll start with a single bond for each, all right? And then if we fill in the other 14 electrons, that gives us 6 there and 6 there, and then we can put 2 on the sulfur. So now our sulfur only has 6 valence electrons, but we're all out, okay? So that means we need to make double bonds, right? That's what we just talked about on the previous slide. The thing is, we could do the double bond from this oxygen to the sulfur or from this oxygen to the sulfur. So if we do it here, we would get this structure, all right? So we have a double bond here, a single bond there. This oxygen has a full octet, the sulfur has a full octet, and this oxygen does. Or we could do it from the other oxygen, all right? And if we did it from this side, the structure that we would get would look like this, all right? So we still have that single lone pair of electrons on the sulfur. We now have the double bond over here. This oxygen now still has 3 lone pairs, right? So they're basically equivalent, okay? And then to draw the resonance structure to complete it, we put brackets around it and we put a double-headed arrow, basically saying both of these work, or it goes back and forth between both of these, all right? And then we know experimentally that what we actually observe is the sulfur having a bond and a half with each oxygen, all right? And then the way we know this is a double bond is shorter than a single bond. So if this was the right structure or this was the right structure, we should see 2 different lengths for our sulfur-oxygen bonds, all right? But we don't. What we see is that there's 1 bond length. It's the same for both of them, and it is shorter than a single bond, but longer than a double bond, right? So it's kind of in between, right? We don't have a great way to represent that with a Lewis structure because it's hard to show that like 1 electron is shared here and 1 is there, and we get this weird 1.5 bond, but that's actually what happens. All right, so that's called a resonance hybrid, and it's just basically an average of the 2 resonance structures that we've drawn. All right, the other extension that we're going to do is exceptions to the octet rule. So boron is the first one. It only has 3 valence electrons. So if we were to make something like boron trihydride, it's not going to have a full octet, and that's okay, all right? It only came in with 3, and it's only going to share with 3 other things in order to make 3 bonds, okay? Hydrogen is the other exception because it only has space for 2 electrons, so rather than needing a full octet, hydrogen just has a duet. It makes 1 bond and then it's done. It's full. All right. The other exception is expanded octets. So an example of that is PCl5. All right. So if we have, if we add up all our valence electrons, we have 5 for phosphorus, 7 for each of our chlorines, so that's 35, which makes 40 total. All right. Phosphorus is going to go in the middle. All right. But now we have 5 chlorines, okay? So if we put those 5 chlorines around the phosphorus, all right, if they each make a bond, now that phosphorus has 10 electrons around it. That is more than 8, all right? So it has more than 8 electrons, which is an expanded octet, and anything that is in the 3rd row or lower is able to do this, all right? And that is because it has available to it d orbitals, all right? So if it's in the 2nd row, the highest energy level is going to be 2, all right? And we know that there's only a 2s and a 2p sublevel in the second energy level, but 3 has S and P and D. So because phosphorus has those extra orbitals available, even though they aren't usually occupied, it's able to take on an expanded octet. All right, and so then if we finish this up, we put electrons around each of our 5 chlorines, all right, and that will bring us to 40 total. So each chlorine has 8, basically, so 8 times 5 is going to be 40. So you can count them up if you don't believe me. All right, so that is our last extension. I hope you found it interesting, and we'll do some more practice with drawing Lewis structures in class.